Okay, I was asked to look at two of the free response questions from 2013 that I assigned. And the first up is number 3, the coffee problem. And so this was what the problem looked like. And the first question we were asked was to approximate C prime of 3.5. Now, if we look back at the table itself, we've got C and time values that are every integer. In order to approximate 3.5, which is right between 3 and 4, we're just going to work with those two values. So C prime, this is part A, C prime of 3.5 can be approximated as the average slope from 3 to 4. So we are going to be looking at f of 4, or I should say C of 4, minus C of 3 divided by the change in t values, 4 minus 3. So C of 4 is 12.8 minus 11.2 divided by 4 minus 3. And that calculation gets you 1.6. And the units of this derivative would be units of C divided by units of t would be ounces per minute. I'll abbreviate ounces. And that's part A. Part B asks us, is there a time somewhere between 2 and 4 when C prime is equal to 2? And when you're asked to find out whether a derivative might have a specific value in an interval, you want to think mean value theorem, because the mean value theorem, if you recall, was the theorem that said that if you have some continuous differentiable function, in this case between 2 and 4, then the average slope between those points is matched at somewhere actually between the points themselves. So, if we take a look at points 2 and 4 and calculate what the actual slope is there, so from 2 to 4, we get C of 4 minus C of 2 divided by 4 minus 2. This calculation gets you 12.8. Now we're at 2, 8.8 divided by 2, and this is 2. So the slope up here is 2. That means that somewhere the slope, which would be the derivative, somewhere in there is going to equal 2. So mean value theorem is the way you prove that. And you do need to state, and the problem tells us, that it is differentiable fully. And we know that if it's differentiable, then it must be continuous. So we do need to state these things to justify the use of the mean value theorem. That brings us to part C, which tells us to use a midpoint sum with 3 subintervals of equal length. We're going to use that to evaluate this integral, actually to approximate this integral, and then explain what it means. So first, we can go back to our data. We're going from 0 to 6, 3 equal subintervals. And so what we're looking at then is we'll do a 0 to 2, a 2 to 4, and a 4 to 6, which very conveniently puts the midpoints at 1, 3, and 5. And the width every time, the delta t in this case, is 2. So we try to approximate this integral. It's going to approximate as a width times the function height, 5.3, plus the same width, function height now 11.2, and finally a last width of 2 and a 13.8. If we add those values up, that gets us 60.6. Then we're going to be taking 1/6 of the integral, which, how convenient is that? 1/6 of 60.6 is 10.1. And the units here are going to be ounces, because if you remember what we're doing is we're finding an average value of the function. The function is ounces. So this would be the average amount of coffee in the cup over the 6 minutes. And we'll just write that real fast. Okay, well, that brings us to the last part, which is part D. And part D says, if we can approximate the function to represent the amount of coffee as B of t is 16 minus 16e to the negative 0.4 t, use the model to find the rate at which it is changing when t is 5. Basically, we're looking for b prime of 5. That's all. And so to take the derivative, we get a 0 here. Here we're going to get multiplying by the derivative of the exponents, the chain rule. So we're going to get a 6.4, the negative 16 and the negative 0.4, and the same original exponential, e to the negative 0.4 t. Evaluate that t equals 5, and that's 6.4 e to the negative 2. And without a calculator, that's the best you can do. Units on this rate of change of coffee amount would be ounces per minute. And that takes care of number 3, and I'll post separately number 5.